Hello, everyone. This is a short recording about some ideas for projects for SIIM 2026. And we talk about some of the problem statements, some of the technology, and potential solutions. And you're going to have to pick one of the following ones, at least one of two. There might be a third one, but right now we only have two defined. So the first one, before we get started, I want to talk about what are the three components of interoperability. First, you have to have a data model. You have to know you're going to send things, and you have to know what you're talking about. So what do those three things mean? First, let's talk about data model. Data model is how does the data relate to each other? How do the objects relate to each other? For example, one patient can have two babies. Those babies can have the same date of birth, but different times. There's probably a check mark that you have to denote them as twins, but there can be other siblings who are not twins. One twin can have blood work every hour on the same date, so blood work can happen multiple times in a single day. People's relationships to each other and medical procedures are super complex. Another example of this is in radiology. A patient can have a radiology procedure which extends over multiple days. For example, cardiac procedures are often done that way, where one part of a cardiac procedure will be done at one time, and then they need to get the drugs which raise the heart rate out of the body, and they need to wait overnight. And then the second half of the procedure might actually be done the second day. So it's an odd situation where you can have radiology procedures which span multiple days, although they're the same radiology procedure or cardiology in that case. Then the second component of interoperability is transport. And it's how are we going to send this data from one system to another system over the wire? And how do we know it's secure? There's things called HTTPS now. Those didn't used to exist once upon a time. That's pretty common, but even then, if you have HTTPS, you have to know what the data format is. You have to understand what the different bits and bytes coming across the network are. So HTTPS is only a really lower layer solution. So the next component of interoperability is transport. Finally, the third component of interoperability is semantics. Medical data is so complex. So, for example, when I say diabetes, measure of diabetes is an A1C value, and that's how much the percentage of blood sugar in your blood. How do I say A1C value? How do I say that I want it as a percentage? How do I say that I want it at a certain time of day? How do I say I want it averaged over a certain time period? Usually it defaults to 3 months. There's link codes for that. So these little pieces of data, like you might think you're just going to send a glucose value. Well, no, you need to know whether or not fasting was involved. You can't just send a glucose value. So medical data is incredibly complex, and you need detailed, very specific semantic codes for that. So those are your three components. You need a data model. You need to know how you're going to transport it, both at the lower layers as well as the higher layers, so that you know what's coming across the wire. And how it's going to stay secure. And then third of all, you need the semantics. Those are the three components. Let's talk international standards for a minute. This is about the data model and the transport. Okay, so first of all, you've got DICOM. DICOM covers radiology, cardiology, pathology, data formats, image formats. It defines a header, which is these little things called attributes. Such one attribute is, for example, patient name. Another attribute is slice thickness for an MR or CT. Another attribute for CT is KVP, or the amount of radiation that a patient was exposed to for that slice. So DICOM defines headers, which is all the acquisition data, and it defines pixels, which is all the actual image data itself. Combining the header plus the pixel data is called a composite object because it can stand on its own and it doesn't need anything else. The opposite of a composite object is when you have normalized objects and they point all over the place to the different objects which are the most up to date. There's pros and cons to both, but when you have a great big enormous set of pixel data, the header attributes look so small that the value of going for all these different resources and links is not as useful. DICOM was started in 1993, but it is updated quarterly every year, and so it is quite up to date. DICOM defines type 1, type 2, and type 3 data, which defines the optionality. Type 1 means it's required. You cannot display an image without this particular information, for example, pixel depth. Type 2 is how to identify the patient. It's useful to know that you can display the pixel data on a screen, but it'd be even better if you knew what the patient medical record number and patient name was. Type 3 in DICOM is ancillary data. And so, for example, maybe it's patient address, things that really aren't as important, but they're really nice to know sometimes. Another example is, where was this image created? That's a really useful piece of information to know, and yet it's type 3. The second international standard that we're actually not going to talk about in this particular hackathon, and yet I want you to know it exists, is called HL7 version 2. It's all the EHR data and the clinical data. So it's the laboratory results. It's your CBC values, your reports. It's based on text and numbers, no images. Think 1980. Think a serial line between two computers. It's text-based. There's no security, and yet it runs 99% of all hospital messages and healthcare systems yet today. We're not going to worry about this one. To be very honest with you, we're trying to replace it. But you need to know that it exists. And it's called, if you hear somebody referring to hats and pipes, that's how you delineate pieces of data, and that's HL7 version 2. The third one that we are going to be working with is called HL7 Fast Healthcare Interoperability Resources, or FHIR. It's a successor to version 2. This is actually version 4. If you ever want to know about version 3, let me know, but we're going to skip it for now too. So this is actually version 4 of HL7. That's version 2, version 4, but we're skipping 3. HL7 FHIR is object-based. This is what defines a patient. This is what defines a report. This is what defines an observation or a lab value. And so it's very object-based, and it uses internet security and HTTP APIs. And so these are things that you know. These are things you learn in computer science in college or even high school, maybe even middle school. And the point of this is being able to use things that are out there on the internet. Why would healthcare define internet security and something complementary to HTTPS when we can use what exists out there today? This stuff didn't exist back in HL7 version 2 days, but now that it does exist and it's firmly cemented into the world, we should use what exists when we can and not try and recreate the entire world. HL7, as opposed to DICOM, HL7 FHIR, as opposed to DICOM, uses normalized objects. That's the opposite of composite. And what that means is that you have to create and access links all over the place. You start with a patient, but then the patient has all these different reports and objects and lab values and all these other things. You have to keep querying for more and more information. There's some ways to get around that using the everything operation, but we'll talk about that later. Here's a catch, though. In HL7 FHIR, everything almost is optional. So you can have an object which is empty almost, and it's correct, but it's useless. So we have to create these things called HL7 FHIR profiles, and that's the way to say, well, for this particular use case, for example, creating a radiology report, if you create an empty radiology report, we're not going to accept that. It's not going to pass, and that's called an HL7 profile. ONC, which is part of Health and Human Services, ONC stands for Office of the National Coordinator of Health Systems, and it's out of Washington, D.C., and they have been creating quite a few of these FHIR profiles, and so that's something that we want to be able to focus on and use, because having an empty object is very not useful. Finally, IHE. IHE stands for Integrating the Healthcare Enterprise, and it combines these standards. It is not a standards body the same way that these are. Quite to the contrary, it'll take a very specific clinical use case and says, now we're going to create a way for a CT or MR modality to query an EHR. So it takes a very specific clinical use case and it solves it using these standards up here. It tries not to create any new standards when at all possible. IHE is not used for research. It is used for clinical daily practice inside of a hospital. Research is a whole nother ballgame, and we're not going to go into that right now. IHE selects from a wide array of international standards and semantic standards. We're going to talk about those in just a second, to profile and get everyone on board for the same way to solve a problem globally. Why do you want to do that? Well, because for one thing, it works better because you have a lot of smart people thinking about it, and it gets globally reviewed. But also, it significantly reduces the cost. So if you are trying to solve some of these problems at your hospital, do you really want to start with a blank piece of paper, or do you want to use something that a whole bunch of people have thought through and have tested in advance for you? and it reduces the time to implement. So that's why IHE is important. We try very hard not to create new standards rather than to use the existing ones and put glue in between the standards when we need to. A lot of times we spend time defining mapping between this standard to that standard. It's what we do quite a bit, actually. All right, semantics. Medical data is so complex. You can't just assume that one value, even though it has the same title, is the same as another value. It's a question and answer pair usually, and you have to make absolutely certain that that question is always the same thing and that that answer represents always the same thing in the same units of measures. For example, how is a measurement taken? So for example, for lab value, for a glucose test or a cholesterol test, you often hear about fasting or no fasting. Well, if you don't know the answer to that, you're going to get wildly different results. And it can do one of two things. It can tell your doctor that you're going on to cholesterol meds this afternoon, or they can say, wow, you had a giant piece of cheesecake for lunch. I hope it was really good. So that whole fasting and no fasting thing on cholesterol tests is critical to know. And yet there's different codes for that, and that's how we know it. So there are many, many code systems that were started at the same time because people had to solve a problem that they had at hand. Subject matter experts all over the world started all these different code systems. So the good news is that we have a plethora of code systems to choose from. The bad news is trying to figure out which code system is the right code system to use for the task at hand. A couple of the code systems that you're going to hear about, DICOM has one too. DICOM has their own code system, DICOM Part 16. But one of the things that you're going to hear about in HL7 is you're going to hear about code systems called LOINC. This LOINC covers lab results, of which there are thousands of different types of blood work and all the other lab results, as well as procedure codes, for example, CT of the head. SNOMED CT covers diagnoses, okay, ignore that spelling error, and conditions. For example, a diagnosis might be, I should actually say type 1 diabetes, not just diabetes, or it should say type 2. That's actually a really bad example. Or it could say myocardiac infarction, which is known as a heart attack, or diagnosis of lung cancer. So not suspected lung cancer, but diagnosis of lung cancer. There's other code systems which are much more specific. For example, RADLEX. RADLEX is specific to radiology and only radiology. It has very nuanced and very specific radiology terms. For example, spiculation is the outside of a margin found on a lung nodule on an MR or CT. So spiculation has a very well-defined definition that you only are going to find in RADLEX, and you're not going to find it in any of these broader terms up here. Also in radiology, there's something called radiology CDEs, or common data elements. And by the way, all this stuff is on the internet. And a radiology CDE is really more of an enumerated value set. And they're saying, all right, you found, what was my example here? You found a nodule on an MR. What are all of the questions you have to answer about what that nodule looks like on the MR scan so that it's consistent with what the surgeon may need? You need to know volume, you need to know longest access, you need to know what the outside margin looks like, because whether the outside margin is smooth or spiculated, which means all squiggly. That's very different indicators for a type of cancer, and people need to know what they're looking at. In terms of the surgeon needs to know what he's about to deal with, or the radiation oncologist needs to know what they're about to deal with. So that's why you need all of these code systems and why there's not only one code system. Another code system that you may have heard of is ICD-10 or ICD-11, which is International Classification of Diseases, which comes out of the World Health Organization. We will use that too. Project number 1, you're going to have to pick one of these two projects. There may be a third project for ejection fraction and cardiology, but right now I don't know enough about that one, so we're going to cover these two. And you need to pick one of these two in the very near future. Okay, you can call this whatever you want, and I would love to know what the metrics are, the rubric for the hackathon this year, but I was not able to attend the first hackathon call. So somebody needs to look that up and find out what rubrics are being measured against. The first one is Cleanup in Bay 5. Feel free to change the title. Here's the deal. There are no DICOM police. There's no DICOM object conformance testing. That's a real problem because you have all these different vendors creating medical images and medical studies. There are hundreds of different vendors creating these images, and they are free to make as many mistakes as they want and still call it a DICOM object, even though the DICOM standard is very specific about what you can and cannot do. These errors are often found at the medical institution when a patient's study cannot be read. So remember that you have a doctor and a patient waiting to act on these results to see what came out of the CT scan, but they're not getting any results because there's too many errors in the DICOM object, and so the radiologist cannot see the images in order to review them. That's absolutely ludicrous. Examples include UID errors. So a UID is a unique identifier. So every DICOM image has a UID. And so you know that image is different from any other image in the world. You can only use numbers. So it'll be like 1.2.840.113.619. something else. And it's this really long string. You cannot use letters in there, and yet you're going to see letters in there, in which case the PAC system, the receiving system, is going to say, yeah, sorry, I don't know what that is, and ditch the image. That's a real problem. We have issues in terms of study identification, anatomy identification all the time. I cannot tell you how many studies I've looked at that says, this is a knee study on the screen, and you open up and you're like, nope, that's a brain. That's a problem because now that image was routed to the wrong radiologist, and you're not going to have somebody who usually reads knees reviewing a brain scan because you need a neuroradiologist for that who's specially trained. Now you have to figure out how to get a knee scan to a neuroradiologist, even though it's not really a knee. These are just there's so many issues with cleaning up these things that would make the world work so much better. And so this is called cleanup in Bay 5. They call them CT bays, MR bays, by the way. That's where the bay comes from. So what are we going to do? We're going to create a configurable pipeline to correct all of these errors. But I would love for it to be configurable so that every site can add something else to their correction list, because heaven knows what all the different issues that we're going to run into. We can't possibly solve them all in a 3-day hackathon. We're going to intercept the images. So today they're sent from a modality to a PAC system. We're going to say, nope, send them to our little app in between. Maybe it's sitting on the PAC system. But we're going to make sure that before they're permanently stored for all of posterity, that we clean them up and correct them. We do need to talk about failure paths because we cannot drop any images, even if, for example, the power goes out in between. So we just need to talk about that. Whoops. Hang on.